week 3. In this week, we're going to be covering an awesome package from Python called Xarray, and this is basically NumPy on steroids. So we can play with any kind of numerical data set. We can do matrices, we can do geospatial data sets. There's a lot time series. There's a number of different things we can do with Xarray, and it's just a one-stop shop for a lot of things with geospatial data sciences in particular. So Xarray is pretty amazing. Before we do get started on that, there's a couple housekeeping things that I wanted to do, and the first thing is we need to download all of the course data sets. So I'm just making my way here to the course GitHub account, and it's also right here from the course website. So we can open up my GitHub, the course GitHub, and we're going to go to this green button right here, code, and we're just going to download everything as a zip file. What this will allow us to do is get every data set as well as all the code, but every data set in the datasets folder in its raw form, which is exactly how we want it. So we don't want any different versions of the file that can sometimes come about from trying to download something from the web like this. So now we have that zip file downloaded, so we're just going to unzip it and open up my downloads folder, and right here it is unzipped. It's called geog 473-673-master, and this is everything that you would find on GitHub. And so now I can go into the datasets folder, and here's all the datasets that I need for the course. So that's how you would go about doing that. So, but now heading back over here, I'm going to open up Xarray here, and let's get started on week 3. So Xarray is an open source project. It's just like with most things in Python. It is completely free and developed for really just multi-dimensional arrays. And so this is what makes it perfect for geospatial sciences, because oftentimes we have a matrix of data, or just a two-gridded array, two-dimensional array. And oftentimes these arrays can even have different levels on them. So Xarray is built on top of NumPy, and it allows for more intuitive, more concise, and less error-prone developer experience. So it's great for netcdf files, CSV files, grib files. It can do just about everything. So before we get started, let's just open up, just like we have before. Let's go ahead and let's open up our Anaconda Navigator, and then we'll double check and make sure that we have Xarray installed and ready to go. All right, so here's my Anaconda Navigator. Remember, I'm automatically on the base environment, and we need to go to that environment for the class that we created called geog38. It's loading in all of the packages and getting familiarized with what we have, and here we go. So I'm going to launch Spider, and then the environments. Notice that I'm on geog38, and I'm just going to scroll down to make sure that we have Xarray installed. So I come all the way down here. I just saw, there it is. Xarray right there. So we're good. We have Xarray installed. This is under the installed tab, so we are good to go here to play with Xarray. So now I'm just gonna reorder things here a little bit. All right, I'm gonna pop open a new file here, and I'm gonna comment out Xarray week 3. So Xarray, as I had mentioned before, is awesome for spatial data. It can do everything from gridded data sets for finance, engineering, geospatial sciences, earth sciences, biological science. It's integrated with other packages that we will get into next week called Pandas, and Pandas is another cornerstone package, a higher level package of Python. It's awesome for input-output operations for netcdf, and it can also do plotting. So let's go ahead and let's load in a tutorial dataset. And so even though we downloaded the datasets that we'll need for this class, this dataset is actually already pre-downloaded for you. So the first thing we're going to do a couple things here. We're going to load NumPy as NP, pandas as PD, matplotlib.pyplot as PLT, and Xarray as XR. So go highlight that, click the white button, and there we go. Everything imported correctly. How do I know that? Because we are now on the second input line, and everything returned successfully without an error. So now we're going to use this special function called tutorial.load_dataset. And so remember, we're using this function from Xarray, and so we actually need to say, hey, we're using this tutorial.load_dataset function from Xarray, which Python recognizes as XR, because that's how we wrote it in. So we're going to go ahead and run that and then print out DS. So it loaded successfully, and we just have a two-dimensional dataset, three-dimensional dataset, and it is latitude, longitude, and then we have some time slices. So we have 25 different latitudes, 53 different longitudes, and almost 3,000 different time slices. And our data variable is air. So it has the dimensions time, lat, long, and it's just air temperature. And then we also have some special data attributes. It tells us the convention, which is coords, a title, which is for time daily NMC reanalysis. We have a description, data is from NMC initialized reanalysis 4 times a day. It's a model, and then gives us where you can actually find this data set. So now what we have right here, if we actually go on and type a type on DS, it's an Xarray data set. So, and this actually gets printed out up top when we actually print out DS. Right up top, it's an Xarray data set. So that's exactly what we want. And remember, this is just built on NumPy, so we can do a couple of different things here. When we call ds dot, we can print out the conventions. We could print out the attributes. All right, there's something interesting going on about that. It's under .attrs for attributes. So that's a little interesting, but that's how this data is stored. So now we have a little bit more. We can actually see the full thing. So we have pressure level values, or sorry, sigma level values. So there's the air temperature at different pressure level values. So then we also have, we can print out the lat, print out the lon, ds.lon, ds.time, ds.air. Gives us a nice little snapshot of the data right here. So there's a couple different things that we can just see based on how this is all stored. So now let's go back to the tutorial and let's just run through this a little bit more. So here's this is exactly what we just printed out over in Spider. So we have our dataset DS, and we have our variable, our data variable, air, and so this is just a little sneak peek of what the data is looking like in air. And here's our coordinates, our attributes, and there it is. This is what I was trying to reference. So we can actually go into the attributes of the specific variable as opposed to the attributes of the data set. So I'm going to copy this over. And remember, for some reason, I can't tell you why, attributes is ATTRS. And sure enough, there we go. We have a long name. We have the units are in degrees Kelvin. We have a grib name. We have a var description, air temperature, level description, surface, individual observations, and the actual range, which is from 185 Kelvin to 322 Kelvin. we can also just completely subselect the values. So let's just print out the ds.air.values, and notice that it's actually now printed as an array. So that's ultimately how this data is stored. It's just a two-dimensional array. And so now if we actually run a type on this, you'll find that at its core, these ds.air.values, when we boil everything down, at its very core, it's a NumPy array. So this is just an example, explicit example of how NumPy is the foundation of Xarray. So a couple cool things that we can do here is we can actually use some functionality within Xarray to help us quality control this data set. And in this case, we're going to use the where function, the .where function on an Xarray data set, which is our Xarray data set is ds. So we're going to run ds.where ds.air is greater than 0. So what this is going to do, let's just run this without saving it. It's going to only print out times where we have values greater than 0. And so the reason that we're doing this is because anything below 0 Kelvin is not possible in our universe as we know it. So all we're doing is we're just getting rid of all those values, and those values don't exist because we already took a look at our data set and our minimum is 185. So therefore this is unnecessary, but it's good practice because there's going to be data sets that you have to load in that have bad data and you're going to have to clean them. So this is one way to do it. So it's the where function. So if I do ds dot and type in wh, all of a sudden where pops up, and when I start the function by using the first parenthesis, it says where we have a condition, and it filters elements out according to this condition. So our condition is ds air greater than 0. So we only want to keep the values where the air is greater than 0. So if I did ds.air greater than 0, prints out like normal, but what happens if I flip it around? I only want the air now where it's less than 0. And now look at our data here. Air went from normal values, normal Kelvin values to nans. So that's what it's doing there. It's just, if it's outside of your condition, it's going to convert all of that data to nan, which is exactly what we want. But in this case, we only want realistic temperature values. So we only want the condition where ds.air is greater than 0. So let's go ahead and let's run that. And this time, we're not only going to run it, we're going to save it. We're going to overwrite ds where ds is greater than 0. So that's why we have ds equals ds where ds air is greater than 0. So now print out ds, and sure enough, the data is looking good. Everything is still the same. Now what we can do is there's a couple other functions here that are really nice, and we can take the mean based on the time dimension. So what this means is we have a two-dimensional data set of latitudes and longitudes, and then we have a time component, which is our third dimension. But what we're going to do is we're going to average out or take the mean of that time dimension. So this data set we see here in our time is from 2013 to 2014. So it's 2 years worth of data. Now, what we're going to do is we're going to average the temperature based on those 2 years. So we're going to average for each point in our two-dimensional latitude-longitude array, we're going to average the time point, the point in time, the temperature in time. So we're averaging the temperature for January days, February days, every day of the year for 2 years. We're averaging that and boiling that down to one single temperature. And this can be done in one line right here. So we say, okay, ds is our data set. It's our Xarray data set. Air is our variable right here. It's our data variable. And then on this variable from the ds data set, we're going to run a mean. And we're going to run the mean on the time dimension right here. Then we're going to save that as temp Kelvin and watch what happens. So I'm going to pop this over here in the console and I'm going to run it. Our time dimension is now gone because we averaged it out. So we went from having, scroll up here, 2920 values, time values, for each latitude and longitude, aka for each grid cell, we averaged that out to just having one single value in time for each latitude and longitude grid cell. And another quick thing that we can do with Xarray that is really nice is we can take our new temp Kelvin data set, and real quick, let me just pop this over here. Let's print out temp Kelvin, and it's an Xarray data array. So now it's not an Xarray data set, it's an Xarray data array. Why? Because we boiled it down. We got rid of some of that extraneous information. We noticed we don't have the attributes popping up. We only have this raw data. So it's just an array that has coordinates of latitude and longitude. I can take this data array and just use a plot function from Xarray on this. We're going to do an Xarray data array dot plot, and our Xarray data array is temp Kelvin dot plot for a nice quick plot. And we go over to this plots tab, and here it is. So you can see here's Canada, here's the west coast, and here's going down into Mexico, here's the Gulf, here's the east coast. So you can kind of see the outline already of the United States of America. So, and this also makes sense because our longitude is right here, we're at minus 40, and all the way over here we're minus 160. And there's our latitude, so we're going from 10 all the way up to 80. So this is North America as we know it from, well, and really part of South America, but this is North America as we know it. And this is just the temperature. So each of these grid cells is the average temperature of our time period. So what we can see is that towards the closer you get to the equator, the warmer the temperature gets and the colder it gets as you approach the poles. So again, look at this. Look at this code that all we had to do here. We loaded it in the data set, we did a little bit of quality control, and then we were able to average the time dimension for each grid cell and just plot it. Just in a couple lines of code, you were able to plot this, and this is a great way to quickly run through some data that you might have just to get an idea of what story this data is telling. Ultimately, that is what data science is. It's taking numbers and writing a story with those numbers. And this is a way that we can paint a picture that tells a story. Warmer towards the equator. Groundbreaking science. So real quick, before I proceed any further, I need to comment things out because I don't want to be that coder that just runs through everything, doesn't code, and then I look back on this in a couple months and think, what the heck was I doing? So I'm going to say quality controlling for values greater than 0 Kelvin. Then down here I'm going to say averaging the time dimension over the 2 years of data, aka 1 temperature per grid cell. And then quick plot of my temp Kelvin data Xarray data array. Cool. All right, moving on. What we can do now is we can also just straight up subtract, just do some array math on this, just like we've done with NumPy before. And we can convert this to Celsius, which can be done by just subtracting the 273.15. So all we have to do here to change every value is just subtract 273.15 from my Kelvin data set, and I'm going to save this new data set as temp Celsius. So I'm going to run these two and check this out. So because of the difference in values, Xarray automatically assumed, and I mean, look at this, there's nothing different. Let's print out temp Celsius. So it's just an Xarray data array. It doesn't know what the units are, but it is assuming that it's in Celsius for us, and that is why it changed the color. It changed it to a blue, white, red color scheme because it assumed that we were dealing with Celsius, which assumed that we were dealing with the temperature. So that is how powerful Xarray is. It assumes a lot for you, and while it's important to know, or at least have an idea about what's going on underneath, what is happening at its core, it's still super nice sometimes when you're just trying to get through some data science and you're just trying to get a quick picture. Sometimes you don't need to know exactly how to compute this on a NumPy level because people have already written these high-level routines where it is already assuming some stuff for us and it is already can make this plot in one line. Now, the only caveat of these kind of plots, they're not nearly as customizable as plotting it straight up with matplotlib.pyplot, which we brought in as PLT, but it's still very effective at getting a quick idea. So now that we have these data sets, can we add them to our original dataset DS? So we have these two data arrays, temp Celsius and temp Kelvin. So there's temp Celsius above, and here's temp Kelvin. So we know we have the same latitude, longitude. We just have different values here. But my question is, can we add these to our original data, Xarray data set DS? So we have this air variable right here, but can we add these other two that we just created? It's as simple as this. So all we're doing is we're saying ds, and we're adding a variable using this string and bracket operators. And we're just saying, okay, temp underscore Celsius is equal to the data array temp Celsius. Likewise with temp Kelvin, and check this out. Now we print out ds. Now we have these additional data variables, which do not notice that it does not have a time coordinate right here. It's only latitude, longitude, and then there is air, our original data variable. Now we can call temp Kelvin from our data set ds.temp, and then we hit tab, and then we have this options. We just want temp Kelvin. There it is. We can print out the dimensions, we can print out the attributes, dimensions, and as we learned earlier, attributes is just a reminder, is ATTRS, so there's no attributes for this variable temp Kelvin, only dimensions. So we can actually add in our different attributes like so. Just like we added these variables up here, it can be the same exact idea behind adding these attributes. So we have temp Kelvin ATTRS attributes, and we're saying we're going to add description like so. Bracket, and then in the string, we're going to name it description, end bracket, and we're going to name the description mean air temperature through time. And let's actually add this. Let's actually add in Kelvin. Run that, and now when I run ds.temp Kelvin, boom, right down here in our attributes, we have a nice description of the mean air temperature, exactly what we wrote over there. So the other nice thing here, the other nice functionality is, let's say that this is all we wanted to do with this particular data set at this time, and we want to save this. We can save it using a function called toNetCDF, which is a great, nice, easy to use Xarray dataset function. So we're just going to save this to a netcdf file called newfile.nc, and you can add whatever path you want. So remember, if you're ever confused about this, come down here, ds.temp to netcdf, and the second I add that first parenthesis, it pops up. We need to add a path, and that is the only thing down here that we need to define. We have a path, we have a file-like object, and then we have an optional path and some other things. But all it does is it just writes this dataset contents to a netcdf file. So I'm just gonna add some quotations. All you need to do here is I can hit D, hit tab, and then here's my different options. Or I can just come back and hit tab, and then this is where Python or Spider thinks I am in my computer. So if I want to save this in my downloads, I can just select D, and then new file.nc. Simple as that. And I'm actually going to copy this over to my script. So now when I go over here to my downloads folder, new file.nc right there. The other thing that we can do with Xarray that's really useful is we can index datasets, just like we did with NumPy. So let's say that what I want here is, let's go back and use our original stuff here. So if I open up ds.air, what do we have here? It's an Xarray data array. So ds is our Xarray data set. ds.air, we're actually querying a variable within this data set, and that is just an Xarray data array. So your Xarray data set is comprised of Xarray data arrays. Now what I want to do is I want to boil this down into, I want to index this by the first latitude and second longitude in every time component. Why do I know that it's stored that way? If I just type in ds, it'll tell me the order in which this data is stored. It is stored time, comma, lat, comma, lon. And as we learned before, the colon operator over here is all. 1 would be the second value in latitude. And 2 would be the third value in longitude. So what I'm doing, just like we did before, I'm using this bracket, colon, comma, means all the time, the 1, aka the second latitude value, and 2, aka the third longitude value, because it's 0 indexed. Print that out, and now check this out. We have a stagnant lat, a stagnant lon, so this is just 1 point. So it'd be 205, so somewhere over here, and 72.5. So we're all the way up here, basically in Alaska. And we have now we have a time series, so we have air temperature for this, right about this point, this pixel up here, for an entire 2-year data set. And we index that like so. If I index something like that, I can again use that nice dot plot functionality. And here we go. Now we have this nice time series of air temperature for this specific latitude and longitude over a 2-year span. So just a really nice thing right here to have, just a really nice, easy thing. The other way that I can do that, so that is really the NumPy way. Just like we did last week in the NumPy tutorial, where we were using brackets and we were paying attention to the dimensions or the coordinates in which they were stored. That's the NumPy way. We can also use the Xarray ways, and this is just a little bit of a more intuitive, easier way. Xarray has a function called .sel, short for select, and we can select explicitly a latitude and a longitude right here. So we saying, okay, give us our ds dataset dot air, so that we want the air variable, and then dot select that variable, the latitude and longitude, like so. So we can run that, and we can also hit dot plot, and it is the same exact image as above. So again, this is the .sel, because remember, Xarray is just an advanced version of NumPy. It's a higher level. And there's our plot. Now, the other thing that we can do, so that is the .select function. We can also index based on the index selection, which is ISEL, or index selection. So I'm just going to come over here, and what we're going to do here is we're just going to create two variables, two objects in Python here. We're going to say lat0 is the 0th latitude and lon0 is the 0th longitude. So if we have lat0 right here, it is 75. Lon0 is 200. So this is the top left corner up here. We were down here, now we're even further northwest. Now what I can do is I can index select, so we know what these values are. Here's my index selection right here. So ds is my dataset, .air is the variable within that ds dataset, then .iselect, or ISEL, where I want the 0th latitude and the 0th longitude. Check this out. We run that, and boom, there we go, 75, 200. Those are exactly the 0th, lat0, 75, lon0, 200, 75, 200. So those are exactly the indexes that I selected right here. So select is great if you have the exact latitude and longitude you know you want, meaning like where you are on a map. The index selection is better if you know exactly where you are in an array. Most of the time, the select function is going to be more useful, but it's important to know that index selection is another version. And index selection is really what we did right here. We grabbed the first, or really the second, because remember we're 0 index, but the 1 value of the latitude and the 2 value of the first index and the second index of latitude and longitude respectively, and we grabbed all of the time. So that's the other thing. We could also grab a time here if we wanted to, and we just need to copy over this exact same format. So it's 2013-0101. So if I wanted to run it like that, and now what we'd have here is we have selected one day for this specific latitude and longitude. So we have 4 values, so we have 6 hours between each recorded temperature. But this is only 1 day of data. And just like before, back to index selection. I was getting a little bit ahead of myself. We can just run a plot just like we did before, and it's the same exact thing. Only a different latitude and longitude, but same exact concept. So we can also do it for other variables here, like temp Celsius. So remember, temp Celsius is we created and added to our dataset ds. So let's index select the 0th latitude, the 0th longitude. Run that, and it pops open a histogram. And why does it do that? Because we have completely gotten rid of our time variable. So there is no time series when we just grab the latitude and longitude like that, because we averaged out all of those times. But we can also select one day like I showed. Only we can, if we just want all latitudes and all longitudes for 2013-01-02, so we're just looking at a histogram of the temperatures on that day. So it's one day, it's all latitudes, all longitudes, and we're just taking a look at the histogram of temperatures. We see our most common temperature is somewhere between 290 and 295 Kelvin. So I'm just going to comment things out here. And remember that we went back to our air variable right here. So we had a number of different times that we could have selected from. Remember that this time does not exist in the Celsius, temp Celsius and temp Kelvin because we averaged that out. And then ultimately we can also select a individual time value that we want to plot. Oops. Ignore that plot and look at this one. So this is only for 2013, this is January 2nd, 2013 at 0600 hours. So this is just a snapshot in time of air temperature for every latitude and longitude, and their time is selected like that. Now, whenever you're selecting time, you really need to focus on the way that the time is stored. In this case, this time is stored as 2013, or as 4-digit year, dash 2-digit month, dash 2-digit day, T, 2-digit hour, colon, 2-digit minute. So the way that we know that is if we do ds.time 0, we print out 2013-0101, doesn't tell us a whole lot, but if we do the first value, finally, we have some time, some specific hour dimensions. The reason that there's nothing on the 0th is because it is automatically assuming 0, 0, 0, colon, 0, 0, colon, 0, 0. So we can just select this, or we could also just pop over here and write 0, 0, and we have a slightly different plot. So it just doesn't explicitly print this out, but it is assuming that whenever you have just a year-month-day, it assumes that you are at 0, 100 hours, 0, 0, colon, 0, 0. So that concludes running through this Xarray tutorial. What I'd like you to do for this week, and this is the first assignment that we're going to do, is using the tutorial data set above, we're going to complete the following. We're going to plot the 200th time dimension. So figure out what the 200th time dimension is. Plot that, just like we did right here. Then you're going to plot a time series of Newark, Delaware. So here is your latitude and longitude. So we're going to create a time series just like this for Newark, Delaware. And then we're going to compute the average temperature for Newark, Delaware over the time series, and we're going to plot that as a histogram. So we're going to be looking for something like this. You have every tool that you need within this tutorial, so try and run through this again if you need to, but that is really all you'll need to actually get through this class assignment. And I'm actually going to change this, so if you notice that this changes, it's a little bit different. I'm going to change this from saying exercises to class assignment, just so it's a little bit more explicit.